have a good look at these. If you've done a little bit of work with linear equations, 3x plus 4 equals 12 or whatever, you look at these and you go, oh my god, we've got x's on both sides. Don't panic, okay? It just means one extra step on top of other things you already know how to do. So what we need to do first is get all of the x's onto one side, and we do that in much the same way that we get rid of whole numbers when we're trying to get x by itself. So let's have a look at this. I've got a negative x over here, and I've got 3x over here. So if I wanted to get rid of all the x's, it doesn't really matter which side you work with, but usually try and make it easy for yourself. In this case, I think if I just add one x over here, that negative x and that positive x will cancel each other out. There'll be no x's there at all. Now, if you have been paying any attention at all, you know that you need to do the same thing on both sides in an equation. Otherwise, it's not an equation anymore. It would be an inequality, because if you change one side, it's not going to be equal. So I have to do the same over here. I need to add another x over here. So when I do that, 3x plus x is 4x plus 7 equals 15. And this is your run-of-the-mill two-step linear equation to solve. So I'm going to take that 7 away on both sides. That's going to leave me with 4x being equal to 8. And I can solve this by inspection. 4 times something equals 8, x equals 2. Over here, no big deal. Looks slightly more complicated. That's just because we're going to have to do some expansion first before we can get rid of the x on one side. I need to expand, collect like terms, get rid of the x, and then solve the equation. So over here, that 5x, nothing's going to change there. Negative 4 times 4 is negative 16. Negative 4 times negative x, two negatives multiplied together, makes positive 4x. That's going to be equal to x plus 12. Collecting like terms, I've got positive 5x, positive 4x. I've got 9x equals 16. Oh, not equals. Sorry. Take 16 equals x plus 12. Again, I could do whatever I want here in terms of getting rid of x. I could choose to take 9x away here, and then I'd have to take away 9x on the other side. But if I think about that, if I'm taking away 9x over here, I'm going to end up with negative x's, and that just adds unnecessary complication. So it would make more sense to take away one x from both sides and get rid of the x on the right-hand side. So I'll do that. Minus x over here, minus x over here, 9x take x is 8x, negative 16 still there, and that's going to be equal to x take x is no x, it's just going to be equal to 12. Alright, solving for this, I've got to add 16 to both sides. If I do that, 8x will be equal to 28, 16 plus 12, and that means, this one doesn't look very easy to solve by inspection, does it? Because it's not going to be a whole number answer. So let's just do it. I'll get rid of that x that's being multiplied there by dividing by 8. I said get rid of the x, I meant get rid of the 8. Get rid of the 8 by dividing by 8 equals 28 divided by 8. So x is equal to 28 over 8. I can simplify that fraction. I know 4 goes into both of those very nicely. 4 goes into 28 7 times, and it goes into 8 twice. And you can leave your answer like that. You can leave it as 7 over 2. That's, in algebra, we tend to leave things as improper fractions. I could change that to make it 3.5. I could change it to make it 3.5. But when you're working with algebra, it's often easier to leave things in fractional, as a simple fraction, even if it is improper. You'll see why probably later when you're doing other things with like x over 4 and such. Okay, I hope that's been helpful.